A warning light illuminates on the center panel. Amber at first, then red. 3 letters. ENG fire, engine fire. Not a sensor glitch, not a false alarm. A confirmed fire warning on the left engine at 35,000 feet. The captain's hand moves immediately. No hesitation, no announcement to the cabin, no time for either. He reaches for the fire handle, a large red T-shaped pull handle set into the overhead panel. He pulls it. In that single motion, fuel flow to the engine stops. Hydraulic pressure to the engine is isolated. Bleed air from that engine is cut off. The engine's generator disconnects from the electrical bus. The fire suppression system arms. All of that. One pull. Less than 1 second. The engine is now isolated from the aircraft, and the fire is still burning. Now, the captain rotates the handle. A pressurized cylinder of Halon, a halogenated fire suppressant, discharges directly into the engine nacelle. The fire warning light goes out. Total elapsed time from first warning to suppression, under 90 seconds. The passengers in the back felt a slight change in engine noise. Nothing more. Nobody screamed, nobody knew. And that is exactly how this system was designed to work. Here is what makes this genuinely surprising. An engine fire at cruise altitude sounds like a catastrophic, unsurvivable event. The instinct says, fire plus jet fuel plus 900 kilometers per hour of airspeed equals the end of the flight. That instinct is wrong. Engine fires are among the most extensively engineered failure scenarios in commercial aviation. Every component involved, the detection system, the isolation sequence, the suppression agent, the nacelle structure, was designed from the beginning around the assumption that this would happen. Not if. When. And the system that handles it is so effective that the majority of engine fire events in commercial aviation are resolved without a single passenger ever becoming aware one occurred. To understand how, you need to understand where fire actually originates in a jet engine and why the nacelle is the first line of defense. A jet engine operates at extreme temperatures. The combustion chamber reaches approximately 1,500 to 2,000 degrees Celsius during normal operation. The high-pressure turbine immediately downstream operates in gas temperatures exceeding the melting point of the nickel alloys it is made from, sustained only by internal cooling air channels that flow through the blade walls. These temperatures are normal. They are the designed operating state. The fire risk does not come from the combustion itself. It comes from fuel or oil leaking into the hot section of the engine, the zone surrounding the combustion chamber and turbine where external surfaces reach several hundred degrees Celsius, a fuel line fitting that works loose, a seal that fails under thermal cycling, a hydraulic line that chafes against a hot surface. Any of these can introduce flammable fluid into a zone hot enough to ignite it. This is the engine fire that the detection system is designed to catch. Not the controlled combustion inside the engine, but uncontrolled combustion in the spaces surrounding it. The fire detection system consists of sensing loops, thin tubes filled with a material whose electrical resistance changes with temperature, routed throughout the engine nacelle. These loops run around the entire circumference of the hot zone through every compartment where fire could initiate. When any section of the loop reaches the fire detection threshold, typically around 300 to 400 degrees Celsius depending on the aircraft type, the resistance change is detected by the fire detection controller. The warning triggers on the flight deck within seconds of fire initiation. 2 independent loops cover each engine, a primary loop and a backup loop. A single loop fault does not trigger a fire warning. Both loops must agree, or a specific pattern of disagreement must occur before the warning activates. This dual-loop architecture prevents false alarms, one of the most operationally disruptive events in commercial aviation, while ensuring genuine fires are detected immediately. Now let's examine what the fire handle actually does. The fire handle is a single control that triggers a sequence of actions across multiple aircraft systems simultaneously. When pulled, the fuel shutoff valve for that engine closes. Fuel from the wing tank to the engine stops flowing. Without fuel, the fire has lost its primary source. The hydraulic shutoff valve closes. Hydraulic fluid, which is flammable under high pressure, is isolated from the engine. The bleed air valve closes. Hot compressed air from the engine compressor is no longer routed into the aircraft pneumatic system. The AC generator field relay opens. The engine generator disconnects from the electrical bus. The engine fire suppression system arms. Rotating the handle in either direction discharges one of two Halon bottles directly into the engine nacelle. The two bottles, left and right rotation, give the crew two attempts at suppression. If the first discharge extinguishes the fire, the second bottle is retained. If the fire warning reactivates after the first discharge, indicating the fire has reignited or was not fully suppressed, the crew discharges the second bottle. If both bottles are used and the fire warning remains active, the crew has exhausted the onboard suppression capability. The procedure at that point is immediate diversion to the nearest suitable airport. The engine is already shut down and isolated. The fire cannot spread to the fuel system. The aircraft can fly and land normally on remaining engines, but the fire must not be allowed to reach the wing structure. And this is where the nacelle design becomes critical. The engine nacelle is not simply an aerodynamic fairing, it is a fire containment structure. The firewall, a certified fire-resistant barrier, separates the hot section of the engine from the pylon that attaches the engine to the wing. This firewall is certified to contain a fire for a minimum of 15 minutes without structural failure. 15 minutes is the design assumption for the maximum time required to detect, suppress, and isolate an engine fire before it threatens the wing structure. The nacelle walls in the fire zone are constructed from titanium or stainless steel, materials selected for their resistance to sustained high temperatures. Drainage holes at the bottom of the nacelle allow any accumulated fuel or fluid to drain outward rather than pooling in a zone where ignition could occur. Ventilation keeps the nacelle interior below ignition temperature during normal operation, so that minor fluid leaks evaporate before reaching the firewall. All of this, the detection loops, the firewall, the drainage, the ventilation, is a passive defense system that operates continuously during every flight without crew intervention. The fire handle and suppression system are the active response. Together, they create a layered defense that assumes fire will initiate and systematically eliminates every pathway by which it can spread. Now, consider the certification requirements behind this system. Before any commercial aircraft receives type certification, its engine fire protection system must pass a series of tests conducted by the manufacturer and witnessed by the regulator. One of the most demanding is the fire test. An actual fire is ignited inside the nacelle under simulated flight conditions, elevated temperature, pressurized fuel flow, airflow through the nacelle replicating cruise conditions. The fire detection system must detect it within a defined time. The suppression system must extinguish it with a single bottle discharge. The firewall must contain the fire for the full 15-minute certification duration without structural failure. If any element fails, the design must be modified and retested. A fire protection system that passes certification has already experienced a real fire in a controlled test environment and performed exactly as required. This is why engine fire events in service so rarely escalate. The system has already been tested under real fire conditions. The crew procedures have been trained to the point of reflex. The redundancy has been designed in at every level. The fire warning that illuminates on the panel is not the beginning of a catastrophe. It is the activation of a system that was designed, tested, and certified specifically to handle exactly this event. The captain who pulled that fire handle was not improvising. He was executing a procedure practiced in the simulator every 6 months, backed by a system certified to contain and extinguish the fire on an aircraft designed from its first drawing to keep flying safely after one engine stops. The passengers felt a change in engine noise. They landed 40 minutes later at a diversion airport. They walked off the aircraft, and none of them knew that while they watched their films and finished their meals, a fire had started, been detected, been isolated, and been extinguished at 35,000 feet in under 90 seconds. If you want to understand what happens when the fire cannot be suppressed, when the uncontained failure tears through the nacelle and the crew faces something the suppression system was not designed to handle, I've covered that scenario in full detail in another video.